Hello and welcome to the Engineering Dynamics Course Companion. We're on Class 14. We've just begun the Kinematics of Rigid Bodies in Class 13. Now we're going to deal with absolute and relative velocity. So this is like the main rigid body velocity lesson. As always, you could go down to the description down below and you could see you can click on the links to jump to the examples. There'll be quite a few things to discuss here. So let's go through them today. We'll start with the bottom line up front. The main thing that we want to focus on is to create this diagram we'll call the velocity diagram to analyze the rigid body motion to depict this combination of translation and rotation of objects. The velocity diagram is like this graphical representation that shows that we have relative motion between 2 points on an object. And we could use either of the 2 points as like this reference point that is the translation part. And then once we use that reference for the translation, we'll pick that point and we'll rotate about it, right? So we can represent that action by way of these, I lost my mouse. Where'd my mouse go? Anyway, we could use these equations right here to represent there's the mouse back there, where this is the translation and this is the relative velocity between the 2 points, and that allows us to get the velocity of the other point. And we could use either of the points as the reference point. And there's several approaches to solving the velocity analysis using this velocity diagram. There's 3 specific ones that we'll cover. I didn't list them here, but we'll talk about them here. Now, okay, I'll say we'll use like vector solutions to the things. We'll use vector math. We can use vector triangles, and we can also use the velocity diagram and use the components as we pick apart the velocity diagram. Those are the 3 methods. And in the next class, we'll see that we could actually solve the same problem using something called the instantaneous center of rotation. But that's in the next class. So this relative velocity, I'm going to use the boomerang as the visual for this right here. So Newt Dog has this and he releases it, right? And as soon as he releases it, it's velocity, right? When it's in his hand, it's accelerating, but as soon as he releases it, it's moving with a velocity here. And it's translating as the boomerang is across, and it's rotating at the same time. So you can see these points A and B on this boomerang are the things that we're going to keep track of. So what we do, and each of those points, they're going to have a different velocity. One is going to be larger than the other. And the velocity diagram is made up of the result, and we say that it equals translation right here, right? Where we take, and in this case, we're going to start off with, we're going to use B as the translating reference right there, right? So velocity B, and we take that velocity and we put it onto A. So if it's in pure translation, both of those points, A and B, have to be translating at the identical velocity if it's in pure translation. If A is different from B, it has to rotate, right? So the pure translation part of that diagram right there, we set the velocity at A equal to the velocity at B, right? And then we add the rotation to it by pinning it. We take and we draw it pinned at B because that's the reference, and we rotate it about B. And that has a velocity that's perpendicular to the line that's drawn between A and B. We call it RA with respect to B, right? So if you want to find the velocity of A with respect to B, that's going to be perpendicular to that line between the two, right? And we write this out as an equation as the velocity of A, that's the one we want to find, is equal to the velocity of B, the reference translation, plus the relative velocity right here. Result, translation, which is the reference, plus rotation, which is the relative motion right there. So when we're writing on an equation, it's for a particular point. In this case, we're writing the equation for A, and we're using B as the reference. Now, we could instead use the other way around. So here's the one we just did, right? Where we showed B as being the reference for that. right here. So we wrote the equation. That equation is written for A using B as the reference. Instead, we could take A as the reference right here, right, and have B as be the thing that we're writing the equation for, right? So in the translation diagram, we took the velocity at A right there, and we put it onto both points, and then we pinned it at A, and you can see that it has the same rotation right here, right? There's the same rotation in both approaches there, but now we've written the equation for that bottom point right there. And we will get the same results overall by either approach. So it might be easier to do one way than another, depending on it. So we could solve this a problem that in terms of vectors by using this relative motion equation right here. And recall back when we introduced relative motion in particles, I said that it was going to be a very important, powerful, simple but powerful equation to try to analyze things, especially in rigid bodies. So if we're going to use vectors, what we do is we replace, and I introduced this in the last class, that relative velocity is going to be equal to the omega crossed with the relative position. And you note that there's A with respect to B in this relative velocity, and there's A with respect to B in that relative position vector right there, that we cross those two. Now, if we were to set this up as a generic problem right here, the results that we would want to get is velocity of A, which we know is made up of components that are multiplied by the unit vectors. And the thing that we know, presumably the reference, is velocity B, and that also is components multiplied by the unit vectors I and J. Now, if it's in two dimensions, we have the omega as a vector. It's just the omega magnitude multiplied by k. So it's rotating about the vector, that's the unit vector that's coming out of the screen or out of the page. And the relative position vector is going to be those distances RAB in the x direction multiplied by the unit vector I, and RAB in the y component by j. So if we were to put these into this equation right here, right, we would place all those into the equation. We would note that we would need to distribute that cross product. So if we distribute that cross product, notably, these are right here are magnitudes, right? Coefficients. So it's actually what we're doing is we would be crossing the k and the I and the k and the j. Now, the k crossed with I turns into positive j. Right. So what we do here is, and I have a diagram in the book where I show all the different combinations. But here, what we want to do is we want to use our right-hand rule, right? And in this case, we're crossing K, right? We're taking our fingers and crossing them. We're crossing K into I. Right, there's I, here's K, and here's I, and we use our fingers and cross them like that way in there to cross an I, and we see that our thumb is pointing in the positive J direction. But now we go to this next one. We're going to cross K with J, right? And so if we're crossing, we use our fingers and we rotate upwards, and it's right hand, and we cross our fingers up from K into J, and we see that our thumb is pointing in the negative I direction. So K crossed with J is negative I. And then we distribute these out. We collect the I's together, and we see here is the results that will happen if we plug these in, right? Now we can also solve these with vector triangles. Right, so the velocity diagram is necessary for this to envision this. We see that, okay, so if we take the velocity of B as being the reference, and I made it longer here, and I said the velocity of A with respect to B is completely horizontal with the arrangement that I've chosen right here. And you can see now the velocity of A right there is that velocity of B right here plus there, right? So we've written that there. So here's the vector triangle. Now, once again, we could use the other as a reference, so let's take a look at that. By the way, this is going to be the velocity of A with respect to B, whereas this is the velocity of B with respect to A. So it's important that we keep that distinction in here. In this case, we're going to say that we know what the velocity of A is going to be. And so we take that and we take the velocity of B with respect to A, which is again, right, it's pointing to the right. And now we were able to find B. And whereas these will give you the same interrelationships between them. Now the next method is, I call it the using the components of the velocity diagram, and I think this is my preferred way to solve the problems. I like vector math. It's an important thing to do, but a lot of times you can lose some of the sense of what's actually taking place. The vector triangles are good, but quite often it requires you to use the law of sines, the law of cosines, and you might lose what's actually taking place there. But I like this method, and then to check it with the velocity triangles. And that's a lot easier to do because now you're just checking to make sure that the triangles make sense. So making an accurate drawing with the proportions, maybe using a ruler and scaling things can be very, very helpful in doing this. Okay, so here is a generic velocity diagram. Instead of using the boomerang, I picked one where the velocities will maybe make it a little bit of a larger triangle when we're done with the thing, but you can help. All right, so we were writing out, we want to find the velocity of A, and we know the velocity of B, so we have this relative motion of velocity of A with respect to B from there. So what we do is we take the x direction of this, right? So here's the equation that matches up here, but we are actually looking up at the diagram, and in the x direction here, right? So we look up at the x direction. We see that we have the velocity of this guy right here, that component of, and we're writing it for that top point A. We could see that for the velocity of B, we could see, and I drew, by the way, I made this positive right here, even though my vector was negative. Okay, so a lot of times for the one right here that's unknown right here, I'll just assume that it is in the positive direction here, and then I'll find out what my answers are going to be right here for the velocity of A in the x direction and the velocity of A in the y direction. I'll put those down there where I'm writing out the equation. But now I will zoom in and I look and I'll see, okay, this one shows in the x direction, right? So that's the velocity of B in the x direction. And then this one right here is the velocity of A with respect to B in the x direction right there. And that's negative because it's negative in the diagram, right? And then I know that the magnitude of VA with respect to B, right? I'll draw it as a magnitude. I know that it is simply omega AB, and then I'll call it RA with respect to B. But a lot of times it's just, we will just replace that with whatever the length of the thing was, right? So maybe I would write what the length of it was just LAB, right? That's the magnitude of the thing. And then I would multiply it by the cosine of this little angle that's inside there. And I would know that angle quite often because I would know like what this angle was right there. I would know that it would be the same onto the thing. And then in the y direction, I do the same thing. I take the velocity of A in the y direction, and I'm going to set that equal to the y component of this right here, this VB in the y direction, and then also this guy right here, this VA with respect to B in the y direction. And those are both positive because of the way that it's written out, and then I replace that with that omega RAB times the sine right there in this case. So I could stick them back into the vector into the vectors if I wanted to, but this is the diagram method as part of this. Well, let's take a look at this. But one of the advantages of doing it this way, I think, is, especially compared to the velocity triangles, is that it also works well. We're going to do the same thing in acceleration. And it gives us a better idea of what the individual components, what their contribution to the whole thing is. So it's a good idea to try to do it know how to do it in each way. It'll help to reinforce what's physically taking place. All right, so here's the example that I chose, and I believe I do this in the instantaneous center of rotation in the next class as well. So, excuse me. Link ABC has wheels at A and B. And these, for some reason, stay in contact with the horizontal and vertical surfaces. And the dimensions, as given, are 4 feet. This is 4 feet long right here. And this is 6 feet long, so it's a total of 10 feet long. And at this moment, it's at a 25-degree angle. And we happen to know the velocity at B is equal to 1.5 feet downwards. And we want to determine the velocity of point C. Like a simpler problem would be to ask you to get the velocity at A, but we're going to ask you for the velocity of C, which will require you to do something with the velocity of A, just to be aware. So we could try with this vector math, and the strategy is to collect what we know. And so we know the velocity of B, and we also know the constrained direction of velocity A. And we do that so we could find the angular velocity. With rigid body motion, quite often that's going to be one of our important things to do, is to find that angular velocity. It's necessary to do. A lot of times, even in the acceleration problems, one of the first things we want to do is find the angular velocity, and then we can proceed and then find the angular acceleration, and then find the acceleration that we want. So just be aware, we're often in many problems looking for the angular velocity. So when looking to try, how should I go about solving this? Look for how do I find the angular velocity is often one of the very first things we're trying to look for. All right, so we write out the equation for what's taking place with the velocity of A, knowing the velocity of B, right? So we write out that vector equation, and then we'll write out the things that we know. We know, and I'm keeping them as symbols for this right here, right? So we have the velocity of A, that's actually the thing that we want to find, and we know that that's entirely in the x direction, so it's just its magnitude, its speed, VA, times I. And then this is actually a given, but I left it as a variable. Velocity of B is negative VBJ, right? And then we can also predict that omega ABC is going to be clockwise, right? That just makes sense. So I'm keeping this as, I'm putting it in as negative. Its value, its magnitude times K. It's rotating about K axis. And then also, this negative is because it's in the A is in the negative direction with respect to B, and then also and we're using a cosine for the thing, and then this is sine, right? So I put these knowns into this equation right here, right, and proceed to go through and do the vector math. And now I'm left with this relationship right here. Okay, so I've done the vector math. Let's say I've done the vector math, and now I collect all the i's. It looks like to me like I did skip a step, which I don't like doing, but I did it in here. Yeah, I usually, well, I guess yeah. Okay, it wasn't too bad because there wasn't many that i's and that j's. Oh no, I did right here. Yeah, no, I didn't collect it right here. So here is the i's right here, and here's the j's. Right, so I want to separate those out. So I collect the unit terms, and a lot of times you might want to do the I first, but then you're going to find that you can't find what you want because you still need to know the omega. But what's key here is in the j direction right here. We only have 2 terms, right? We have this guy and this guy, so we're able to find this omega. That's an unknown. So we plug in the numbers, and we're able to find that omega ABC is 0.4138 radians per second. Now, in the I direction, because we weren't actually asked for the velocity of A, we don't actually need to find this, but we'll go ahead and do it anyway. So in the I terms right here, we collect those I terms right here. And because we know omega, we're able to find what the velocity of A is, and that's 0.6995 feet per second. And that's going to be to the right. All right, so now let's see, we wanted to determine the velocity of c. That's actually what we were asked. So we write out the velocity of c, and now we could actually use a as the reference if we wanted to, but we're going to use, go ahead and keep using b, right? So we wrote out the equation, and here, and I went ahead and I left these, by the way, as being positive. Right, is I won't make an assumption about what direction they're going to make, and we'll just see when they come out negative, you know they're in the negative direction. So the assumption when you don't know is quite best to just choose the positive direction. Once again, we know what that is, the angular velocity, and here's the relative position of c with respect to b, because c is the thing we want to find. So we write out the equation here. And then we do the cross products, and then we group the things together, or we rewrite the thing out, and then we look in the I direction, and we could just plug in the values, and we will find that we have a negative VC in the X direction. So that makes sense. It's kind of moving in that way right here because the thing is rotating down that way. So you would expect that C has to get closer to the wall. Okay. And then J, we plug this, the values in, and we get a negative 3.75 feet per second. And that makes sense too because that's, of course, it's going downwards right there, right? So now we have the X and the Y components. We should get the magnitude of it, and we should get what the direction is, and then we should write it out. And once again, want to be careful that we're make sure including the quadrant symbol in there, that this is going into the lower left-hand quadrant. Now we're going to redo the example. This is the example being done with the velocity components of the velocity diagram. Okay, so what we'll do is we'll write out the velocity diagram, right? And we can include what we know right here, right? We do know that that's going to be in the horizontal direction. And so we write out the y direction first for this velocity of a right here. And we happen to know, just looking at it here in the y direction, that it's 0 there, it's negative b right here, and this one is going to be, because it's rotating this way, is going to be times the cosine, right, of that theta. You've got to be careful where, and that's probably the hardest part in here sometimes, is determining where that angle is going to be. So working through there, we find the angular velocity of this thing, which is the same as we found in using vectors. And then in the x direction, we're able to just look here and say, okay, here's the VA, there's 0 right here, and then this one is going to be positive, and it's going to be times sine of theta. And we're able to find, and we get the same thing for the velocity at A. Now for the velocity at C, we write out that equation again, and I'm going to make a new drawing for this as opposed to reusing or trying to clutter up the other velocity diagram. So I'm using velocity at, looking for the velocity at C, using B as the reference. So in the y direction, I didn't necessarily have to use the y direction, but I went ahead and I did anyway. And actually, I think that should be the x direction, right? Because it says right here. So here you go. Found another mistake. There's the x direction, and we take the velocity as c. And by the way, this right here should be. There's another mistake. That should be c. Right there. Velocity is c in the x direction. It's going to be equal to 0 right here in the x direction, right? And then it's going to be negative right there because of this, right? See, because it has a negative component right there, and times the sine of theta. So plugging those values in of the knowns, we get that negative 1.049 feet per second, which is what we got from the other one. Now, and this says the x direction, whereas this should be the y direction. Darn. And then, okay, so right here, we're looking for this guy, and we take, boom, boom, boom. This should be a negative value right there. That should be negative. And then this should be, yes, okay, so this is correct right there. So we got something correct. And say the velocity is c with respect to b. And putting those values in there. Okay, here this is correct right there. There, see, that's negative. That should have been negative right in there. We get that negative 3.75, which is correct. All right, so we get the magnitude and the direction of it again, and we find they get the same thing as we had before. Now, lastly, we use vector triangles, right? Velocity triangles. And so here we're writing out. I write out the diagram again, but we use the velocity diagram of point A at this time, right? So here is this is known. Right here. So this is the known guy right here. We want to find this one. And we don't know the magnitude of VA with respect to B, but we do know the angle, right? So the two knowns of this are the velocity of B and its angle, obviously, and the angle of VA with respect to B. And that's enough for us to be, and we also know the direction of VA. So that's enough for us to figure out what the relative velocity is going to be. Because this is a right triangle, we don't have to use law of sines or law of cosines. It's just a basic right triangle. We could just find the velocity of A with respect to B by dividing the velocity of B right here divided by the cosine of theta. And we find the relative velocity. And we know, and by the way, if we wanted to find velocity of A, we would just take the velocity of B and take it times the tangent of this angle. That's right in there, right? And we would be able to find it. We don't need it, but we found it anyway. And then if we want the velocity of A with respect to B, we know that it's omega times LAB. So now we just divide the velocity of A with respect to B by LAB, and we find what that angular velocity is, right? And now for the vector triangles for the point C, a little bit more complicated. I'm using the velocity diagram here to try to arrange this right here. So we write the thing out and we take a look. So we know the velocity of B, and we know that it's going downwards, and we know the angle that it has to go, right? It has to go there, right there. So by drawing that thing out, what we can do is we could find the velocity of, we could find this magnitude, right? Because we know omega and we know LBC. And I wrote out beta from this is just going to be 180 degrees minus that 25. So we know what that is. So we could use the law of cosines. Why can we use the law of cosines? Well, we have two sides, and then we have the angle that's formed between them, right? So now we could find the length of LVC by taking the square root of VB squared plus VCB, VC with respect to B squared, minus 2 VB VC with respect to B times that cosine of beta, right? So make sure you review that law of cosines. Will help you find the unknown in there, right? So we find this, and we find the magnitude that we had from the previous methods. And then from the law of sines, we could mess around. We could find these angles, and here's the unknown angle. We're going to find this is the unknown angle that we're going to look for, and we could find that it's going to be 15.63 degrees, but we need to subtract that from the horizontal because if you recall, we really want to have it be a quadrant that comes from the horizontal when we report it. And we find that 90 minus that 15.63 is the 74.4. And therefore, we have it all three methods. I know, it's a lot of material to cover in one class. The vectors, you should be able to go through and use the vector method. You should be able to go through and do the triangle, but you should also have this velocity diagram. So we'll get into some more opportunities to try that out because we have to do this often also in the acceleration classes. So for more examples, and we really need to work through a lot of examples to be able to own this right here. We have the Engineering Dynamics Course Companion, Part 1. This is the particles, but now we're into Part 2 for with rigid bodies, right? And these are available from Morgan and Claypool Publishers. If you go down to the links down below, you can have links to get them. You could also find them on Amazon.com. And you also consider subscribing to the channel. I will produce some more videos coming up. I believe this is class 14. There's 10 more, so there's 24 classes total. And thank you for your time. See you soon.